Hello, welcome. This is now the last Excel D1 tutorial. Okay, this is on linear programming. Now, it might sound ridiculously difficult. I'm just here to obviously tell you what the hell it is, but it is a very, very simple topic, especially compared to the previous algorithms we've had to look at. And the key thing with this is it's, I think, one of the only topics, if not the only, I have to double check on that. I probably should know that, but anyway, there's no algorithm to it. Well, almost there is, in the sense that there's a method to follow, but it's not like the algorithms we've looked at previously. It's not really defined as an algorithm. Okay, so in this video, what I've done here is I've tried to draw this graph, and essentially what it is, it ranges from 0 to 20 in the y-axis and 0 to 20 also in the x-axis. Now, I've drawn it to that. I'm not necessarily going to use all of it, I'm just drawing it to that. But basically, we've got an objective function here that says z is equal to 24x plus 16y. And I'll go into what that means in a minute, but that's what the objective function is, and that function, we've got to look at it inside these constraints where 2x plus 3y must be bigger than 9, or equal to, x plus y must be less than or equal to 13, and x must be bigger than 0 and y must be bigger than 0. But then the last two are obvious because that's what we can see on the graph there. Okay, now they will also tell you that they'll draw the graph for you, but if they didn't, they would say the graph will lie where x is, x and y between 0 and 20 each, okay? So you'll draw a graph like that. I don't think there's anything else really. No, but just a recap actually, just be saying we're going through on this video. Okay, we're going to essentially go through this question, okay? And give you a bit of an idea of how to shade out different bits. It's all about shading this and finding something we call the finite region. Okay, and I'll be showing you in that finite region how we do something called maximise and minimise this objective function. Okay, I'll also be just maybe doing an extra question on that so you can have a go at yourself. So after I've gone through one, I might put one on the board for you to have a go at yourself. I'll see how we go for time, because the last video was, I think it was about 2 hours, so you're probably quite dead from that if you've watched that. And I can hear some of your jaws dropping if that's not on there yet. I suppose that'll take 7 years to upload to YouTube, but anyway. Then I'll just be going on to the latter part. Is one of the questions they might ask is to formulate the linear programming problem. In other words, I've told you what the constraints are and the objective function is. They might not tell you that. They might give you a paragraph of information and ask you to come up with these constraints. And then, after that, I'll be just iterating, going on, about how we can combine all two, to produce a third method, okay? So they might not tell you the constraints, they might not draw the graph, they might not tell you the objective function, but ask you to, they will tell you the objective function, but they won't tell you constraints, and they'll ask you, well, where is it maximised and where is it minimised? So basically, that last little bit combines the first bit of how I'm going to show you how we can show a minimising and a maximising of that on the graph, okay? And the second one is to actually draw them, come up with them constraints yourself from a bit of information. And then the third is combining all of it, as I said. So coming up with the constraints and then finding the region, a finite region, and then maximising or minimising this function. Okay, so the first thing that you need to do, well, whatever this function is going to, if you were to just draw that function out, well, you couldn't because you don't know what x and y are. But you could say, well, we need to know what z are to find out what x and y is, even just to find x, okay? So obviously we can't just draw that on, and you will never draw the objective function on. You might have to be aware of what it looks like. So if you were to look at that as a graph, as a line, sorry, if you wanted to draw, now you wouldn't draw the objective function on, you wouldn't do this. But if you wanted to, what you would do, well, whenever you see a normal gradient, that's going to be a straight line, quite clearly, because z is just, it's going to be a value, it's not going to change, okay? So you would rearrange it, so you'd get 16y is equal to 24x take z, okay? and then y would be equal to 24x, take z all over 16. Okay, so therefore your gradient would be 24 over 16, and I think that's 3 over 2. 3 over 2. Okay, so your gradient would be 1.5. Now, that would be your gradient of a line. Now, the reason we can't draw that on there is because, well, z is, the intercept is z over 16, and we don't know what z is, so we can't have the intercept. But you would just imagine it pushing it outwards. But anyway, we'll go into that in a minute. We know that's, what I'm saying is, all these constraints, we have to acknowledge them on the graph. So we can show what area does it lie in. In other words, what are the x and y coordinates this objective function could potentially be. So the first thing we need to do is actually draw these constraints on the graph. We have to show them physically. Okay, now to do this, we can't say, well, 2x plus 3y is bigger than 9. That's not an equation of a line that I've ever been familiar with. Well, you can think of it, because that you don't necessarily think 2x plus 3y equals 9, is bigger than or equal to 9, is going to be some kind of straight line. You think, this is an inequality. Well, to draw it on a graph, what you would do, okay, because that's a constraint, remember. That's just a constraint. It says 2x plus 3y must be bigger than 9, okay? So you think of it as 2x plus 3y is equal to 9, okay? Because what it says is 2x plus 3y must be bigger than or equal to 9, okay? So therefore 2x plus 3y is equal to 9 because it can be equal, because it's greater than or equal to. In essence, we've got to draw this line on the graph, okay, and then shade out whichever bit we don't want according to the constraint. Okay, so we'll just draw this graph and I'll tell you which side to shade in a minute. Okay, so obviously you could simply just work out what y is when x is 2, 4, 6, 7, whatever. But the easier thing to do is just work out the intercepts, what this equation. Now, you could make it equal to 2 plus 3x, take 9 is equal to 0, but what's the point in that? You simply say, well, it crosses the y-axis when x is 0 and crosses the x-axis when y is 0. So let's look at the y-axis first. Now, when it crosses the y-axis, x is equal to 0. So therefore, 2 times 0 plus 3y is equal to 9. So 3y is equal to 9. So y is equal to 3. So it crosses the y-axis at the point 3. So you put a dot on the y-axis at 3. Okay. Now, for the x-axis, for the cross the x-axis, you need y to be 0. So 2x is equal to 9. So therefore, x is equal to 4.5. Now, that's where it'd be more helpful to have a proper square piece of paper. Okay, but I've kind of drawn it quite helpfully there. So you put it somewhere in between 4 and 5. Okay. Now, actually, one quick thing. Now, if you were to draw the objective function on the graph, a quick way of doing it. Now, I said you could rearrange it into the form y equals mx plus c. But another way of doing it, if you wanted to draw the objective function, you wouldn't. By the way, I can't stress this enough. You wouldn't unless it asked you to. Obviously, you would just switch the numbers around. So it would cross the y-axis where. Cross the y-axis at 24 and then cross the x-axis at 16. In other words, you switch the numbers around. So z is equal to 24x plus 16y. So it cross the x-axis with the number that is next to y, and it will cross the y-axis at the number next to x. Okay, but as I said, it's not asked you to draw it on, so I wouldn't. Anyway, so we've got the first constraint here, and we said that we can turn that into a straight line, which will look something like this. As I said, my drawing's not perfect, but you get the idea. You would draw that as that's really crap actually, but that's just because I've not got a square piece of graph. Now we need to on linear programming. Whenever you draw a constraint in, you need to shade whichever side you don't want. So then you'll have an unshaded finite region. Okay, so we're told that 2x plus 3y must be bigger than 9. Now if you're not 100% sure straight away, what you could do is you could just pick any point, okay, which is on either side of the line, and whichever point either side of the line doesn't fit, you shade that side of the line in, because we don't want that. Now quite clearly, because it must be greater than that, it must be on it's the right hand side that we want, so we shade the left hand side of this line in. So, but you could just check that. So if we say 2x plus 3y must be greater than 9, if we pick a point, say 2, 1 here, 1, 2, where x is 1 and y is 2. Well, 2 times 1 is 2, 3 times 2 is 6, so 1 plus 6 will be less than 9, so it's not going to be on the left-hand side, so we shade the left-hand side of this line off. And you may be going, well, we haven't considered all the other constraints yet, so why the hell can we just start shading off areas? Well, if it doesn't, even if some of that area that we've shaded off fits one of the constraints, okay, we can't have that area because it doesn't. We need an area that complies with all the possible constraints, okay, all the constraints that's given. So we need to shade off the area that doesn't fit that, and even if it fits all of the others, because it hasn't fit the first one, okay, trying to get away there, because it doesn't fit the first one, fit one of the constraints, we can't allow it to be in our finite region, because we need the area that eventually we're going to get that fits all the constraints, because we've said that this objective function, we're looking at where it's maximised and minimised, but we'll get onto that later on. We need to look at the area where the subjective function is allowed, okay, and it fits all these constraints as well. Okay, so any value in that area that we end up finding will be equal, it'll have an x and y value, okay, and then we can attribute it to this objective function. Okay, so let's just, okay, so apply the same principle now. So we've done it for 2x plus 3y, and that's bigger than or greater greater than or equal to 9. Okay, so we want the right hand side. If you want to have a go at the next few, now as I said, for the last two constraints where it says x is bigger than 0 and y is bigger than 0, all you have to do is just shade off that area where it's not bigger. But as I said, it doesn't really matter because they won't give you that on the exam. Okay, so if you just want to have a quick go now at drawing a line in for that constraint, so the x plus y is equal to less than or equal to 13, you can have a go at that. Sorry, I'll just have a go at drawing that. That blue line is going to be the first one. Okay, so just give me a second and pause the video if you want to have a go at drawing that line in there, and then obviously we'll come up with our objective function, finite area. Okay, so I've drawn the line on that. Hopefully you did too. Okay, so we've got the y-intercept of 12 and the x-intercept of 13. That's for the line x plus y is equal to 13. But we're told the constraint is that x plus y must be less than 13. Well, as we shaded the left-hand side for a greater than, surely we shade the right-hand side when it's less than. Well, that's obvious. But as before, if you're not 100% sure, do pick a point. But remember, we've already shaded off all of that area there, so you can't pick a value or a coordinate, per se, in the region where we've shaded off, because it might fit this constraint that we're concerned with, but it definitely doesn't comply with the first constraint, because that's the area we crossed off, and we need an area that matches all constraints. Okay, so anyway, hopefully you shaded out the right hand side of this line. I was thinking of doing that and just putting it straight up, but I just wanted to give a bit of an explanation to it. Okay, so this is now our area, and I'll highlight kind of the outside of this area in red. Sorry, it's not perfect, but you get the idea. Okay, so what we've got here is the area which I'm going to label the area R. Okay, and that's our finite region. Okay, now that might be a question you get asked, just draw the finite region, in which case that you would stop there. But as maths is not that easy, we've got this is our objective function here. Now, as I said, the gradient was 1.5, in other words, it's 24 over 16. Okay, and now because we're not 100% sure what z is, the cheap way of doing it is saying, well, down this curve, this z, it will intercept the x-axis with the number in front of the y at 16, and it will intercept the y-axis with the number in front of the x, 24. Well, that's not on our graph, okay, what you would do is you would just work out a line with a gradient of 1.5, and you would essentially, I mean, I'm not it's not the best idea because I've only got, I can really hold 2 pens to this. Okay, it will be a gradient something like this. That's not the best idea. Okay, where you've got a gradient and the line would go like this, and what you would do, okay, is see which one it passes through last. Now obviously, as we know, the line would be endless, but I can't obviously do endless. So anyway, it's obviously going to be one of the maximums, okay? In other words, one of the corners of this little shape we've got here, okay? So it's either going to be that corner, that corner, that corner, or this corner, okay? In other words, it's going to be one of the intercepts, okay? Where these two graphs, okay, these two constraints, it's going to be where one of them intercepts a certain axis. Now, to prove, it depends obviously if it was asking you for maximum or minimum, but either way, it's going to end up at being one of these corners. Okay, so you might want to sub in each value, each point of the corner into this objective function and see which gives the biggest result. Okay, so obviously this point here is point 0, 12. Okay, this point here, one of the other points is 13, 0. This point here is 4.50, and that point there is 0, 3. Okay, so obviously their coordinates, so you sub the x or y value into this objective function, and whatever it's asking for, it's asking for the maximum. Well, obviously you choose the point which gives you the biggest value for z, and obviously it's asking for a minimum. Logically, it's the smallest value of z that is found. Okay, so it's very kind of simplistic. Alright, so as I said, all questions will generally have that sort of theme. Now, maybe picking the points aren't so difficult. So I'll give you a few types of variations you might get asked on this. In other words, a few variations of what you might have to do differently to find out what x and y are to sub in. Now, one of the ways that you would do, okay, if you've got two, you might have, it might not be the simple way, you're just looking at the intercepts. You might have one of these points, might be where two curves intersect, or two straight lines intersect. And to do that, you can either make the two equations equal to each other, okay, so simultaneous equations with substitution or cancelling, okay, or you could simply look at your graph and you could see one of these points, okay, one of where the intercepts, and you would draw a dotted line off to the x and the y axis, okay, seeing what x and y were at that point, okay, and then you would sub them values into your equation. In other words, if you had two curves that intersected, okay, so what I mean is you might have a curve like that and a curve like that, okay, so you would do a dotted line off, and that was 17, you'd do a dotted line down to 4, okay, so that's obviously the point 4, 17, okay, and then if that was part of your objective region, one of the corners, you would sub 4, 17 into your objective function, just like you would do for one of these points that I've coloured in green. Now, and bear in mind that might not make much sense, but really that's as hard as all of that gets. Now, that's just one side of the potential questions they could ask on linear programming. Okay, the next couple is all about coming up with these constraints yourself. It's very easy, just simply drawing it on a graph, and they will always give you a graph to draw on, so you don't need to worry about coming up with the axes. But one more thing actually on this before I rub it off and we go to the next question. You may get a question which is such that you get a constraint, say 24x plus 200y, okay, it's less than or greater than 9, and or something like 2x plus y is greater or less than 1,000 or whatever, and you might get a y value which is not on our scale. So what would you do then? Because obviously, without working out every single point, okay, on the graph, okay, you'd be very hard pressed to draw the line like we have done here, okay. So what would you do then? Well, obviously we will have maximums on our graph, say the maximum value of y or the maximum value of x, okay. So what you would do then is just say, well, this is what our maximum value of y could be. What's our maximum value of x at that point? Or you would just choose one of the maximums, okay, of x or y and see what the curve was at that point, okay. And you would choose 2 points, 2 maximums for a curve, okay, and then you would just connect them with a straight line, because you will never be given any other constraint that isn't a straight line. I haven't seen one anyway, so hopefully that makes sense. think I'll just, one sec, I'll actually just try and come up with an example to match that just on this graph, because I don't think that's a particularly brilliant explanation. Okay, so I've come up with this other potential constraint we could have. That quite clearly doesn't fit on the graph. Well, almost. We've got this constraint that says, say, I've just put this hypothetically, okay? 7x plus 2y must be less than 400, and you go, well, it will be all over the graph, because there's no point that looks like it's anywhere near 400. But we still have to check in a normal way. Okay, so I'm going to check where it crosses the y-axis, and we know where it crosses the y-axis, x is equal to 0. Okay, so 2y is equal to 400. Okay. Oh, 7x. Sorry, 7x plus 20y. So that wouldn't work. So 7x plus 20y must be less than 400. So therefore 20y is less than 400. So therefore y it must be less than 20. So it crosses the y-axis at 20. Okay. So you put a blob on the y-axis at 20. But this bit would already be shaded out. Okay. But I'm just going to unshade it so you can see where this line will go. Okay, so let's do the same for x. Well, 7x will be less than 400. And if you work out what x is, x will be something like 52. Quite clearly, we don't have that on our graph. So what we do instead is we just come up with a value for y. Okay, we just pick a y value. Now, likely it's not going to be a low y value, i.e. it's not going to be a y value of 6 or 2. It's because if you put 6 or 2 into that, it'd be 20 times 6, and that would be divided. And then you take away 400, and you divide that by 7. Okay, and it's still going to be off the chart. Okay, so basically what we need is quite a high y value. Okay, so basically what I'm saying here is if we want to work out the x value to sub, and we have a very high number, we need to sub in a very high y value. Okay, so I picked 20 and then 19, 18, went through. And the first one that I came across that kind of worked was 15. So I subbed in y to be 15. So we say let y is equal to 15. And when you did that, it's 7x plus 20 times 15, which is 300, is less than 400 or equal to it. So therefore 7x is equal to 100. So therefore x is equal to 14.3. Okay, and to get that value, put y to be 15. Okay, so we've got a coordinate there of 14.3 and y to be 15. And we've also got y to be 20. Okay, now this reason this doesn't fit with this graph is because we've already shaded all of that to the right there. But if we were to draw this line on as well, which we wouldn't because this bit's already shaded out, okay, but you would still draw it on if it mentioned it, okay. So we say it intercepts the y-axis at 20, so obviously x is 0, so you plot y to be 20. However, the only other value you can pick of x is 14.3, okay, which is somewhere up here, okay, and where y is 15. So you do a dot across there, and y is 15. So it's, as I said, it looks something like that, okay. And then you'd obviously shade on the right of there because we need it to be less than 400. But obviously we've already shaded all that bit out as well. So I'll just go over all my working out. But hopefully you can see that was kind of pointless because we'd already drawn a line through a shaded area. But in the exam it would be a bit more pronounced than that. In other words, it'd be a bit more obvious. Okay. As I said, that's kind of a scary scenario to have, where you have a line which when you work out the x and y intercept, it's not on your graph. You can't just extend your graph because there won't be room for that in the exam. So that's kind of a cheap method to do. Okay, so hopefully that makes sense. And what I'm going to do now, that's the first part of the linear programming problem done. Okay. The other potential type of question you might get asked is, well, come up with these constraints yourself. So what I'm going to do is just rub this off the board now, and then I'll move on to a potential question, okay? And I'll just put some bits of information on the board and we'll talk through it and see how we can come up with our own constraints, okay? So hopefully you've got all that, and I'll just pause the video and it magically go away. Hello, welcome. Oh. Well, it's not really hello and welcome. as I've just kind of found this other question. Now, what we've looked so far is linear programming in terms of just simply abiding by some constraints, drawing, obviously having a graph drawn for us, and then just finding out the finite region, using that to work out the maximum and the minimum of this objective function. Now what we're going to do in this question, now this combination, I think, it combines you being able to come up with your own constraints, draw a graph, and then find out the maximum or minimum of a function. Now, I know I said I'd break it up into two separate questions after the first one. One being coming up with your own constraints, and then the second one kind of working out, drawing your own graph and making up the making up the finite region. Well, not making it up, going from the results. But I thought, you know what, sack that, I can't be bothered, I'll just stuff it into one question, because at the end of the day, you'll be doing it in one question anyway. Anyway, so this question I've picked, it's talking about Gary the Gardener. Friggin' hell, first time I've not seen, it's a nice name, I can understand that. Not the usual ones you get in exams, because they feel they have to be, you know, they have to do equality and stuff, but whatever. Anyway, Gary the Gardener is to plant a garden with a combination of palms and conifers. He is to plant, so we're given a couple of sentences of wording, weirdly enough, just to tell us what we can and can't do. Okay. Now, obviously, we're going to have to turn this into some kind of equation so we can come up with constraints. Now, the two is going to plant a garden with a combination of plants and conifers. Now, it's up to you what you, because obviously we need to put these in the context of algebra, okay? Because obviously that's what the constraints are in terms of algebra, and we can't just simply write plants and conifers all the time. It's going to get boring, okay? So what we're going to do instead, obviously we're going to need to put one on the x-axis and one on the y-axis. So it's easy just to say x and y. You could call them P and C, but putting that on a graph, it might a bit confuse you. So it's totally up to you, but I'm just going to call it x and y. So, okay, so I'm going to call the plants, the palm trees. I'm going to call the palm trees, I'm going to label them as plant X, okay? And I'm going to label the conifers as plants Y, okay? So whenever I refer to X and Y, I'm talking about X being the palm trees and Y being the conifers, okay? So anyway, he's told that he can plant no more than 80 palm trees. He has to plant at least 10, but not more than 40 conifers. He cannot plant more than 100 trees in total, sorry. Each palm tree needs 20 litres of water to be nourished, and the conifer needs 60 litres. There are 3,000 litres of water available each day. Gary makes a profit of £2 on each palm tree and £1 on each conifer he plants, and he wishes, this is the key bit, to maximise his profits. So when we talk about maximising minimising a function, okay, we're going to be maximising the function. That's what whenever you see maximise profits, that means we're going to obviously end up all these constraints, and we're going to have to come up with our own the objective formula is just a formula which is what they want to achieve. Okay, in this case, because he wants to maximise his profits are going to be the objective function. Obviously, we're going to have to come up with one in terms of an equation for the profit in terms of x and y, and he wants to maximise it. So we're going to have a finite range region even. I'm going to have to find the maximum for this function inside it. Okay, so let's take into account all the information we've been given. So the best way to do that is in some kind of a table. Now, because there are so many different, there's so many different questions on formulating your own linear programming problem, I can't simply say this is one question, now it's going to be exactly the same for all. Now the method will be the same, but spotting what to put in, because I'm going to come up with a table so I can lay all these bits of information out rather than just simply noting them all down. You could do that, but I find putting it in a table is a bit more easier. But if you can't put it in a table, it's completely fine. But I'm going to give you a bit of a heads up of how to do that. And obviously, as we go through past paper questions, it's going to become obvious what you put in a table. Okay, so what the two columns even are to do with the two things that you mention. Okay, in terms of what are the two things that are being considered, or it might be more than two, but generally it's only two. Okay, so in this case, the two things being considered are plants and conifers, X and Y, whichever way round you want to put it. And each row will therefore be a different kind of constraint. Okay, so the first row would be to talk about the fact that the first thing it mentions is how many of each type of plant is going to plant. Okay, so this might make sense. Probably choose my wording here. I just put the first row as the number. Okay, number. So the first thing we're told is that you can't plant more than 80 palms. Okay, but obviously you can plant up to. So therefore we need an equation that relates x up to 80, but we can have x less than 80 as well. Okay, so it's up to and including 80. So therefore, okay, that's what you'd write in that column. Okay. However, he can plant 10, but he can't plant more than 40 conifers. Now you can come up with this as a combined equation, okay, to say essentially y must be between, it must be greater than 10, it can be greater than or equal to 10, but it must be less than or equal to 40. And that obviously you can split up into two, because we're going to have to draw this on some kind of graph, so maybe that's not so easy to draw on the graph. Okay, so you might want to put y is bigger than or equal to 10, but y is less than or equal to 40. Okay, but as I said, either way you want to put it. I'm going to leave it as that, and then we'll split it up later. Anyway, he cannot. The next thing we're told is he cannot plant more than 100 trees in total. Okay, so you would put the third column is kind of the overall constraints. Okay, so in this context, I would put x plus y. Okay, because x is the number of palm trees and y is the number of conifer trees. Well, it's not the number; it's just a variable associated with the palm trees and a variable associated with the conifers. It might be number, water, whatever. Okay, and that must be less than or equal to 100. Okay, so that's the first little bit out of the way. Each palm tree needs 20 litres of water a day. So the next bit talks about the watering they need. So that would be your next column. So be about watering. Okay, so it tells us each palm tree needs 20 litres of water a day. Okay, so rather than writing 20x, I would simply just write 20. Okay, because we're talking about litres of water here. I'm not talking about numbers, so we'd have to include x. You could put 20x if you wanted to, but that might confuse you. Okay, because just like for example, if this was a results table for science, or if you do science, even you wouldn't write newtons, the force, at the top of the table, and then for every value you write in the table, you wouldn't therefore also write newtons, because you wrote it at the top of the column. In the first row, you wouldn't write it in each row. Okay, so anyway, that's why I didn't put 20x there, but you can do it if you want, because it's not exactly physics. Anyway, so the palm tree needs 20 litres, whereas the conifer needs 60. Okay, but there are only 30. Sorry, there are only 30. There are only 3,000 litres of water available each day. Okay, so you will put therefore x plus y must also be less. Is that the way they put it? Sorry, one second, double check. Sorry, I'm just double checking. Sorry. Put 3,000. Okay. So 20x plus 60y must be less than 3,000. Okay, because each plant, in fact, the reason why I put 20x there, actually you did need to put 20x, is because it's for every x plant, for every x palm tree, okay, you need 20 litres, so you times it by 20 for each conifer plant. Whereas Y, you need 60 litres, so you do 60 per every plant, so 60 times the number of plants. Okay, and the total must be less than 3,000. Okay, we're also told that Gary makes a profit of £2 on each palm tree, so the next row is about profit, so the profit received on each tree. Okay, £2 on each palm tree and £1 on each conifer, so you simply just put £2 in that one and £1 in the conifer. Okay, so it all looks quite simple so far. Yeah, so what we have to do is formulate a set of constraints to represent this problem. So we've kind of already done that. So we just need to spot all the constraints we've put down in this table and write them down. So I've circled all of them there. Okay, so you can see how we've got them constraints. I mean, as I said, you could have just read the information and just picked out the constraints, but it's not so. It's a lot easier and it's more easy to make a mistake just simply spotting it. But if that's your kind of thing, then you know, well done to you. Okay, so the next is B, part B, is state the objective function. Now the objective function, remember, is relates to what they're trying to achieve. We're told that Gary wants to maximise his profits, so it's going to be to do with profits. Now the total profits of his venture are going to be made up by his profits of his palm tree and the profits of his conifer tree. Okay, and we're told for each palm tree he receives £2 and for each conifer tree he receives only £1 profit. But just like we did here, where we had for every palm tree we needed 20 litres, so we did 20 times every palm tree we sold. Palm tree we sold for every palm tree. Whereas for the conifer tree we had 60 litres, so we did 60 times the number of palm trees. Similar thing here, but instead of litres to water, it's profit on each one. So therefore, the total profit, or the objective, which is labelled as P, is 2x plus 1y, or 2x plus y, and that is the objective function. Okay, so that's your answer for part B. Part C says, Henson find the optimal solution to his problem, stating clearly how many of each type he should plant. And it tells you the graph should be between 0 and 100 for both x and y. Now, it's wrote as this, by the way. Okay, that's what it's wrote as. When it talks about the graph being between 100 for x and y, that's how it's wrote in the exam. So basically what that means is you could put x or y there and it's between 0 and 100. Just the examiner's been lazy and they're not writing this instead. And this. Okay, so basically what I'm saying here is that one and that one combined will give you that. Okay, so that's just what the inequalities mean. So hopefully that makes a bit of sense. But as I said, that's just how it's drawn. Anyway, that was just telling you about how big to draw the graph. Okay, so because we need to find the optimal solution to this problem, don't be put off by the fact that trying to sound intelligent. But you just have to think linear programming problem. What have we done to be able to answer this question? Okay, so I probably have to get up. Oh no, I don't. That's good. Alright, so you say, what do we have to do to be able to answer this question? Well, the only thing we've done, that's about, he wants to maximise his profits. So, what is his problem? His problem is, he wants to maximise his profits. Well, we've just come up, you should just click in your mind that we've just, in the previous part of the question, we've just stated the objective function. So we need to use that objective function in the next part of the question. As with maths, the one part of the question leads on to the next part. Obviously, as long as it's part of the same question. Okay, so obviously what we need to do, therefore, is draw some kind of graph. Now, as I said, it will be drawn for you in the exam, so maybe it won't be so not as obvious. Okay, so you simply draw a graph, okay, with values ranging from 100, it's 0 to 100 on both the x and y, and I'm just going to go at drawing this. Okay, because I fear I might probably make a mistake if I try and talk through it. Right, Sorry about that. So I've drawn the graph with the values from 0 to 100. I just didn't want to do it with my back to you. It's not the smoothest. Okay, so we want to maximise this function. So we draw all of the constraints just like we did before. Okay, so we've got x plus y must be less than or equal to 100. Well, as before we just did, well, where's it intersect the x-axis, where's it intersect the y-axis? Well, quite clearly if we made x 0, y would be 100, and if we made y 0, x would be 100. So it's just, you put a point on the x-axis of 100, and on the y-axis of 100, and join them up. Okay, and because we want x plus y to be less than 100, we need to shade the right-hand side of it. Okay, and as I said, with all these, you can always just double check by putting a point outside the line, checking if it works. If it doesn't, then obviously it's inside the line. You want to shade outside of it. Okay. The next what I'm going to do is these two. Okay. Now I've labelled it singly as y's between 40 and 10, including. Okay. So therefore you could shade. You could just think of that immediately like that, or you could split it up and say y must be greater than 10. So you draw a line y equals 10, and you shade everything under it. Okay, and also we know that y must be less than or equal to 40, so you draw a line of y equals 40 and shade everything above it. Okay, so that's what we've shaded so far. But we also need to consider the fact that x will be less than or equal to 80. So you draw a line up, x equals 80, and shade everything to the right of it. Okay, so now what we've got here is this region. Now I'll kind of shade in for you. So I'm going to just draw. This is what I would advise as well. Get kind of a green pen or something, and just colour in kind of all the outline of this finite region. Okay. So as I said, this what we need to do is maximise his profits. Okay. And this is his profit formula, okay, so it's 2 times the amount of palm trees he sells plus the amount of conifers he sells, because he gets £1 for every conifer and £2 for every palm tree he sells. So as I said previously, it's going to be at one of the corners of this shape, okay, so you can just check. So it's going to be 0, 40, 0, 10, and then so just looking from the graph, okay, that's going to be 40, 70. Now, as I said, you could just see where the line x plus y is equal to x plus y is less than 100, and the line y is equal to 40 meet. Okay, in other words, sub it in, and then you'll get your value for x, or you can just read it off the graph. Okay, so obviously that is about 65, 40, but as I said, you would need to sub it into the formula to actually find it out. Your other point is 80, 20, and then your final point is 80, 10. Okay, so you sub each one of them into the formula, and I can't really be bothered doing it, and just you will get the maximum of the point where it is 80. So we double check. Where you sell 80 palm trees and 20 conifers. Okay, and you just sub that in to your formula for your profit. Okay, and you get your profit to be approximately £360. Now, obviously, you might have it slightly different if you've not used graph paper, and you just assumed it off of your graph. But obviously, on your graph paper, it would be exactly precise. So, it would be around 360. Okay. Alright, so the next part of the question C. Okay, so the next part of the question says, Gary creates a different pricing strategy where generates profit £1 on each palm tree and 4 on the conifer. So this hasn't changed, okay? Our graph wouldn't have changed. We just try, essentially, because it's saying Gary, all he's doing is generate a different price. He's setting a different price for each one. And the same constraints apply, okay, we assume they do anyway, because we're not told otherwise. So basically, you try each new point, okay, and you sub it into this new formula, okay, which is profit on one palm tree, so it's x plus 4y, so his new profit formula is x plus 4y, because he's selling each palm tree for £1 and £4 for each conifer. Okay, and as I said, you just sub each of them extremes into your formula, and then you would get a profit. Okay, so hopefully that makes sense, and I don't really waste too much more of your time going through any more examples, because, well, I think that's alright. But again, if you want me to do some more examples out of this book I've got, please do let me know. This book is just a standard kind of class workbook, really. But as I said, I'll be going through past papers anyway, and I think that's the biggest thing for these. Alright, so thanks for watching, and hopefully it's been helpful. We'll see you in the next video.